This is chapter 2, molecules of cells. We'll just briefly try to go through this, try to keep it as short as possible. I'll highlight the important things that'll be on the exam. So this is matter. Matter is essentially everything that exists. This includes me, you, the water that you drink, the chair you're sitting in. So you can typically define matter in 4 different phases, this being a solid, a liquid, gas, and something called plasma. Just knowing that these exist in these 4 states. This is an element. I'm sure in your high school chemistry class you've studied different elements like hydrogen, sulfur, iron, magnesium, all the different elements. So each element has its own unique properties like density, solubility, melting point, and chemical reactivity. Each element is made up of distinct subatomic particles called atoms. That's going to be important later on. But each element in its own simple substance can't be broken down any simpler. So elements are made up of atoms. You have a combination of atoms or a combination of elements that make up something called a compound. And we'll discuss that a little bit later. So like I just said, an atom is the smallest part of an element that displays a property of the element. So this is important. Again, definitions like to show up on exams. Just for our purposes, we can represent elements by symbols. So, for example, whenever you see the letter H, capital H right here, that just means simply hydrogen. Or whenever you see Cl, that stands for chlorine. Again, they're composed of 1 or 2 letters. Nothing else really to say about that. This slide's very important. So each element each atom is made up of 3 subatomic particles, and these subatomic particles are protons, neutrons, and electrons. They each have their own electrical charge. So protons, P for positive. Neutrons are neutral. Neutrons neutral, so that means they're uncharged. And again, it's important to know that protons and neutrons are located within the nucleus of the cell. That's very testable. And electrons are those are negatively charged, and those exist in the outer orbital. They kind of orbit around the atom. So just like we just previously said, protons and neutrons are located within the nucleus. You can see here the nucleus of the cell, and then we have the positive charge right here that's represented by the plus sign, and then you have the 2 electrons on the outer shell out here. So we'll touch on this a little bit later. But within the periodic table, each element has its own atomic number that is assigned. And the atomic number just simply means its electrical state. So for example, helium's atomic number is 2. So this essentially means that helium has it has 2 protons. So the atomic number represents the number of protons that are there. And generally, unless an element is an isotope, which means it has a different number of neutrons, generally, most elements are within a neutral state. So if I were to tell you that helium had 2 protons, that would mean it had 2 electrons as well, because remember, electrons are negatively charged. So in order to make the element neutral, you would need 2 electrons to match its 2 protons. But again, we'll touch on that here in a bit. So really for our purposes on this slide, knowing that protons and neutrons are located within the nucleus, and electrons move around the shell. So again, just like I previously mentioned, the atomic number. All atoms of an element have the same number of protons, right? Same number of protons. This is called the atomic number. That's important. The number of protons in the nucleus make each atom unique. Generally, atoms are assumed to be electrically neutral, meaning the number of electrons is the same as the number of protons. Now, there is something called an isotope, and an isotope means that it has a different number of neutrons. So, an isotope is, for example, carbon is known to have a different number of isotopes. So, carbon usually is represented by it's usually represented by a certain atomic number. The protons do not change, but the atomic mass does change. And the atomic mass is the number of protons and the number of neutrons. So the atomic mass can change, and that simply just means that it has a different number of neutrons. And we'll talk about that um, in a bit. So the atomic number, each atom has its own mass number. Again, here's what I was kind of alluding to, which is sum of the protons and the neutrons in the nucleus. Protons and neutrons are assigned one AMU or atomic mass unit. Electrons are so small that we don't really even figure this up. So, for example, we were just talking about helium. Remember, helium's atomic number is 2. So we assume that it has 2 electrons as well, remember, because we want it to be electrically neutral, but it has 4 as its mass number. And whenever you see this written, um, whenever you see this written um, in this kind of configuration, the mass number is always located to the top left, and the atomic number is always to the bottom left. So what makes up the difference in this mass number? It's the number of neutrons that are located there. When we were discussing an atom independently of the periodic table, the atomic number is written, like we said, to the lower left. Atomic mass number is written to the top left. Really, just the important thing to know about this slide is knowing that the protons and the neutrons, again, are in the nucleus, and realizing that the protons and the neutrons make up the atomic mass unit. Again, you guys aren't going to be chemists. We're not going to go too into detail on this. I'm just kind of highlighting the principles. So an isotope, what's an isotope, right? Again, I was talking about carbon a minute ago. As previously mentioned, each element has the same atomic number, thus the same number of protons. However, the number of neutrons may vary slightly. So I believe this is a picture from your book, or if not, I found it on the web. So carbon should always, always, always have 6 protons, right? Because that's its atomic number. That's what makes it unique. That's the number of protons that it's been given. And generally, carbon, its mass number is 12. Or I'm sorry, its atomic mass unit, or its AMU, is 12. So we would have 6 located here for the atomic number, and the AMU, or the atomic mass unit, is 12, represented by 6 protons and 6 neutrons. So if we were to say that, okay, we have carbon 13 or carbon 14, this would be considered an isotope because it has a different number of neutrons than carbon 12, which is carbon in its most elemental state. Carbon 12 is the most abundant. It's what we find most abundant around us. However, there are carbon 13 and carbon 14 does exist. And the only difference is the amount of neutrons that are here. This is what makes it unique from the most elemental form of carbon, carbon 12. Again, I just want to highlight the principle, and this is why I'm going into detail, just highlighting the principle of what an isotope is. An isotope is just it's just an element that has a different amount of neutrons. It has a different, it just gives it a different number of neutrons. So we'll go on. Again, atomic mass, this is just, again, highlighting the principle. Atomic number is written down here. It's the number of protons in the atom. Definitions are important, guys. Again, I could very well see this being on an exam. And then just seeing the mass number. The mass number is just the number of protons and the neutrons. So this slide's really just highlighting the periodic table. I'm sure you remember this from your high school chemistry class. Um, Chemists discovered a number of elements. Once they realized these elements, they tried to figure out a way to organize them. They did it in rows and columns. So your rows and your columns. Um, the vertical columns are known as groups, and the horizontal rows are called periods. And they kind of did this by chemical reactivity. So um, really, I could go into further discussion on this, but for our purposes, I don't feel like it's that important for what you guys need to know. But group 7 is the most highly reactive because they react with one atom at a time. These are called the halogens. Your book will kind of go into more detail on that, but I'm not going to beat a dead horse on this one. So we'll move on. This slide's important just for definition purposes. A molecule, again, is formed when two or more atoms bond together. So remember, we have atoms. Atoms are subatomic particles. Subatomic particles called atoms come together to form molecules. For example, here I have oxygen just doesn't bond. Just one bond doesn't exist in nature as a single atom. In order for it to form a molecule, it has to come together and form another bond with oxygen. So you never see O1, right? Have you guys ever seen, it's not H1O, right? It's H2O. So in order for oxygen to be considered a molecule, it has to have another bond with itself. When atoms of two or more different elements bond together, they form something known as a compound. So, for example, if I was to give you a question and I said, which of the following is an example of a compound? And I have O2, Cl2, C2H6O, or H. Which of the following of those would be considered a compound? So again, the answer choices are O2, Cl2, H, which is just representing hydrogen, or C2H6O. So you know that would be C2H6O because why? It's atoms of two or more different elements bonding together. So that's just what makes up a compound. All of those are molecules because it's two or more atoms bonding together. Hope you guys are starting to see the trend of this. An ion, right? What's an ion? Again, definitions are important. Ions form when electrons are transferred from one atom to another. So remember whenever I mentioned that we like for all elements to exist in a neutral state, typically. So an ion is just simply a element that does not exist in an electrically neutral state. For example, if I were to have an element that has two protons and two electrons, but again, we know that to be helium, right? We know that to be helium because helium's atomic number is 2, meaning that it has two protons. And we know that it likes to be neutral, so therefore it must have two electrons. And let's say that I say that helium becomes positively charged. Well, in order for helium to become positively charged, what would it have to do? It would have to lose an electron, right? Um, it would have to lose an electron. So one electron is lost, and therefore I would say that helium exists in the positive state. So just kind of highlighting what an ion is. So I say here that ions are formed when electrons are transferred from one atom to another. I have here an example, sodium. Sodium has only one electron in its valence shell, right? Tends to be an electron donor. Once it gives up this electron, the second shell with 8 electrons becomes its outer shell. Again, these shells aren't, again, if you were in high school chemistry, you probably learned about this, but I don't want to go in to it too in depth. The principle of this slide I want you to know is that ions form when electrons are transferred from one atom to another. I want you to know that ions can be positively or negatively charged. They are not electrically neutral. So let's just go over some definitions that we've already highlighted so far, right? So we said that atoms are made up of subatomic particles. They're made up of protons, neutrons, and electrons. Protons and neutrons exist where? Exists within the nucleus, right? Protons are positively charged. Neutrons are neutral. Neutral. Just making sure you guys are paying attention. And electrons are electrically charged. Electrons exist in the outer shell or the outer orbit. And from there, we know that the atomic number is made up of the protons, and the atomic mass unit is made up of the protons and the neutrons. We know that we can have different variations of isotopes, and we know that an isotope always has the same number of protons, right? So carbon, we gave that example of carbon having an atomic number of 6, and then it having different variations in the number of neutrons, which is what makes it an isotope. And then from there, we talked about what makes up a molecule. A molecule is simply a group of atoms joining together, and we give the example of oxygen binding to another oxygen. The subscript O2, meaning that oxygen is bound to another oxygen atom, meaning that that's a molecule. We said that a compound is simply a group of elements coming together, and we said that C2, meaning that there's 2 carbons, H6, meaning that there's 6 hydrogens, and then an oxygen. Those elements coming together forming a compound. So it's good once you go over a few slides just to kind of go back and see if you have that understanding. And I hope that we're all on the same page before we move on. So we'll kind of move on going forward, right? So here I talk about the principle of something called ionic bonding. And all ionic bonding is it's an attraction between negatively and positively charged ions, right? So here I have an example of sodium chloride, right? Sodium normally is very positively charged. So you'll often see Na plus, and then you'll see chloride existing in a negative state. So it's just a complete transfer of one or more valence electrons. Again, not really, don't need to really go into this in huge depth. I just need you to know that ionic bonding is an attraction between negatively and positively charged ions. And again, definitions are important, guys. Definitions, you have to have a solid foundation before we move on. So then we'll go over something called covalent bonding. And whenever you hear the word covalent bonding, I need you to think of shared electrons. So covalent bonding, shared electrons. So an example of covalent bonding that people often use is water, H2O, right? So I say here in a hydrogen atom, the outer shell is complete when it contains 2 electrons. If hydrogen is in the presence of a strong electron acceptor, it gives up its electrons to become a hydrogen ion. If this is not possible, hydrogen can share with another atom, and therefore they've completed the outer shell. For example, one hydrogen atom will share with another hydrogen atom. Their 2 shells overlap and their electrons. So you can see here H2. This is an example of a covalent bond. They equally share the electrons. And next, we'll move on to the properties of water. So we have a few different properties of water, and each of them are going to be unique, and they're going to be important. They'll probably show up on exam purposes. People love to test on the properties of water. So just first need you to understand what calorie is, right? Calories is the amount of energy that is needed to raise the temperature of 1 gram of water by 1 degree of Celsius. It's the many hydrogen bonds that link water molecules help water absorb heat without a great change in temperature. So The reason that water is so good at not changing temperature is due to the strength of this hydrogen bond. This bond, hydrogen bonds are the strongest of the bonds. So far we've talked about ionic bonds, we've talked about covalent bonds, and now we're talking about hydrogen bonds. So this is kind of unique to water, right? I talked about covalent bonding being present within water, but the hydrogen bond is the bond responsible for making water able to absorb so much heat without really the great change in temperature. Again, it's the strongest of the bonds. Um, Water has such a strong bond within hydrogen that other molecules, whenever they are exposed to the same amount of heat, it only takes half as much heat before they will change temperature, whereas water takes a greater amount of heat due to the strength of this bond. So again, this should be water. Water has a high heat of vaporization. Doesn't that make sense? That it would have a high heat of vaporization because of the strength of that hydrogen bond. Um, the heat that water is exposed to has to be so high in order to vaporize. Right? We talked about matter existing in those four states. Right? Solid. Right? So heat applied to that solid makes it turn into what? A liquid. So as more heat um, happens, it's trying to overcome and break these hydrogen bonds. So, in order for a liquid to change to a gas, um, there's going to be so much more heat. That's why, if you think about whenever you're boiling water, right? So, initially you start out, or we'll even use the example of like an ice cube, and then you'll put it on a burner. Let's say you're in the chemistry lab, right? And then you put it on a burner. What happens? You're going to have to take a significant amount of heat in order for it to get to turn from a solid into that liquid. And then what's going to happen once we have that liquid? Uh, as more heat is exposed to it, it's going to begin to rise up into the air as condensation, or sorry, into a vapor first. It's going to vaporize first. Um, so again, that's just due to that hydrogen bonding that happens. We need so much heat in order for it to overcome that um, that we have to put in so much heat in order for us to break those bonds. So again, just kind of want you to realize that it has a high heat of vaporization. Nothing really more important than that on this slide. Just kind of giving you guys some details so um, it helps you better understand. So we'll go on. Water is a solvent, and what is a solvent? So a solvent is essentially just it's just something that is used to break down or dissolve a solute. So a solution contains dissolved substances called solutes. And I give this example here. When ionic salts, right? Ionic salts, like we said, sodium, the positively charged, and chloride, the negatively charged. Remember what an ionic bond is? Uh, it is just an attraction between a positively and a negatively charged molecules are put into water, right? Water is going to act as the solvent. So what are we making? Sodium chloride is just salt water. The negative ends of the water molecules are attracted to the sodium, and the positive ends of the water molecules are attracted to the chloride. So I think over here, I have an example of this, and I have the oxygen here, and I have the sodium here. Really, again, just need to know water is a solvent. So far we've said that water has a high heat of vaporization due to what? The hydrogen bonding. And then I said as well that water is a solvent. So water can break things down. And we know that. We know that from everyday life. Um, Again, this slide's important. Just need you to realize these definitions. Water molecules are cohesive and adhesive. So cohesion refers to the ability of water molecules to cling to each other due to hydrogen bonding. Again, whenever you hear water, I want you to think of hydrogen bonding. So cohesion is simply what allows water to exist as a liquid. Um, so again, Due to the cohesion, water can exist as a droplet, and um, it's able to stick to things. Um, it's able to bond with itself. Because of cohesion, water exists as a liquid. The strong cohesion of water is apparent because water flows freely, yet water molecules do not separate. So water can exist as a droplet due to cohesion. Again, water can exist as a droplet due to cohesion. So adhesion is whenever water adheres to another surface. So cohesion, water is able to exist as a droplet. Adhesion means that water can stick to other things or it can adhere to other surfaces. Again, I'll put a picture in here. It says adhesion occurs when water molecules are attracted to the walls of the vessel element. So it's just simply illustrating that water can exist to other surfaces, whereas cohesion just means water can exist as a liquid or as a droplet. Again, I just have an example here. Adhesion refers to the ability of water to cling to other polar surfaces. That's just due to water's polarity. So polarity just means that it has a strong negatively charged. We'll come up here and we'll see that water H212O, it's due to the negative charge on that oxygen molecule that makes water polar. Remember that water has two types of bond. It has a polar, right, because of the negative charge, covalent meaning equal sharing of electrons. The equal sharing of electrons comes between the oxygen, the O2, the two equal sharing of the oxygen. And where does the hydrogen bond come from? Do you guys know? The hydrogen bonding to the oxygen. And which of the three bonds are the strongest? Remember, we have ionic, which is due to what? Unequal sharing of electrons. Is that the strongest? No, it's not. And covalent, remember whenever I say covalent, we think of what? Equal sharing of electrons, good. And which one's left? And that's hydrogen bonding. And hydrogen bonds with oxygen. So we'll move on, just kind of driving in purposes. This is how I want you guys to study whenever you've been through some different topics. I want you to try to organize it, right? We have three different types of bonds. I know there's ionic, there's covalent, there's hydrogen bond. Remember, oh yeah, which one's the strongest? Oh yeah, that is going to be hydrogen bond. This is how you study. You go through 5 to 10 slides, and then you go back and see what's important. Those slides, kind of group them together. So here we have the purposes of cohesion adhesion. Your book says that it can assist in the transport of nutrients and waste, and it can also contribute to the transport of water and plants. Again, not really that important for our purposes, just want to give you some real life examples. These were things whenever I was studying up to present this lecture that I guess I didn't really realize that I thought was kind of neat for you guys. So ice is less dense than liquid water. This is kind of unique, actually. I didn't realize this, but essentially, usually, well, we'll just read the slide. As liquid water cools, the molecules come closer together. This is kind of unique, right? Temperature below 0 degrees Celsius. When water is frozen, the water forms a regular crystal lattice. This is actually going to be why whenever you put a glass of, let's say that you're putting a bottle of pop in the fridge and it begins to freeze. This is why over time, if you just leave it there, it's going to bust. It's because of this crystal lattice formation. Usually when things freeze, they become more compact. They get tighter, more dense. But actually ice is less dense. So normally when things freeze, they become more dense, right? But actually ice, when it freezes, it becomes less dense than liquid water. And this is due to that crystal lattice formation. So ice, things are going to expand whenever they become frozen. So just need you to know crystal lattice formation. The crystal lattice formation is what makes ice less dense than water. And it's also due to that, what? Hydrogen bonding. So hydrogen bonding, crystal lattice formation, that's important. That's the reason ice is less dense than liquid water. Switching gears. So we'll go through the properties of water again, right? Properties of water, probably pretty important since I went on and on about it. So we know that ice is less dense than liquid water. We know that it has a high heat of vaporization. We know that it's cohesive and adhesive. And we also know that what? We also know that water acts as a solvent. Um, you see something about water and there's an answer choice hydrogen bonding, chances are it's correct. Water has two types of bonds, hydrogen bond, covalent bond. We know that covalent bonds have um, equal sharing of electrons. We know that hydrogen bond is the strongest of the bonds. We know that it's unique to water. We know that ionic bonds is an unequal sharing of electrons. Um, let's see. Let's talk about organic molecules. Organic molecules, there's a whole chemistry section called organic chemistry you've probably heard of, and it's literally the study of carbon and hydrogen. So the term organic refers to the molecules that contain carbon and hydrogen. Um, these molecules are often called the molecules of life, and that's true. Uh, it includes classes such as carbohydrates, lipids, proteins, and nucleic acids, and we'll go over each of these individually. Um, so inorganic molecules, right, are anything that contains any other molecule other than um, carbon and hydrogen. So if I give you a test question and I said which of the following is an inorganic molecule, and I give you um, carbon, I give you CH4, which is methane. Um, I give you CH2O. Which of the following of those is going to be an example of an organic or of an inorganic molecule? Would it just be regular carbon, CH4, or would it be the C2HO? Which one? Right. If you said C2HO, you'd be correct. Because why? It contains something other than carbon and hydrogen. It's inorganic. It contains something else, and it's that oxygen that makes it inorganic. So now we're going to talk about monomers and polymers. Now that we have a good definition of what organic molecules are, we're going to move on. So a monomer is just a large number of subunits, right? A polymer, poly means many. So what does polymer mean? Many monomers. So again, monomer, large number of subunits. Polymer, multiple monomers. It's just multiple subunits coming together. So we have these different monomers and polymers, right? Monomer is just one subunit. Polymers is multiple connected together. They come together to form these things called macromolecules or biomolecules. And all macromolecules are the things in your dietary needs, right? Your carbohydrates, your lipids, and your proteins, and something called nucleic acids. And nucleic acids, what you'll see later on, is what makes up your DNA. We'll talk about that a little bit later on. So I just need you to know what monomers are. There are a large number of subunits. They come together sometimes to form something called polymers. And just realizing that carbs, lipids, proteins, and nucleic acids are something called macromolecules. And we'll go over each of these individually. And those will be all very important. Carbs, lipids, proteins, nucleic acids. I'll tell you the unique properties of them and why they're important. So we talked about a monomer, but how does it become a polymer? Well, it's through something called a dehydration reaction. And a dehydration reaction, whenever you hear the word dehydrated, what do you think about? If you said loss of water, or if you said, hardly any water, then you're correct. And during a dehydration reaction, you lose something called a hydroxyl group and a hydrogen atom. And why does that make sense? Because you're losing H2O, H, and another O. So you're losing water. So I think I have on the next slide an example of a dehydration reaction. So whenever we have a dehydration reaction, we take and we form actually a polymer. So to degrade polymers, once we have a polymer, we add in water. So we remove water in order to form a polymer, right? From a monomer to a polymer, in order to join them together, we remove water through a dehydration reaction. And in order to break a polymer down back into monomers, we're going to do something called a hydrolysis reaction, or we're going to add water. So knowing both of these, um, is probably pretty important. So here we have an example of a dehydration reaction. I have monomers on each side, and then I have the hydroxyl group and I have the hydrogen atom right here. And then I'm removing water, and then I'm joining these monomers together. And then here we have a polymer, right? And then I'm pushing water in and I'm separating it. Um, so now we'll go over carbohydrates. And carbohydrates, whenever you think of carbs, a lot of people think of them as bad things, right? And in excess, they can be, but essentially, we do need them. It's one of the biggest energy sources for living organisms. Whenever you hear the word carbohydrate, I want you to think energy source. They do exist in this configuration here, a 1:2 to 1. It's not really important for your purposes if you're going into chemistry or things, or you're a biology major. I would probably stress this to you, but carbon to hydrogen to oxygen, this is typically the ratio that we see those in. And I have a ration, it should be your ratio. Um, but again, just knowing that it's an energy source, that's sufficient enough. The term carbohydrate includes single sugar molecules, and sometimes we have chains of sugars. And carbohydrates are, whenever it's a single sugar, we call it a mono meaning one, monosaccharide. Saccharide is going to be the root word, mono meaning one, so one sugar. Um, uh, pentose, meaning it's a monosaccharide with 5 carbons. Hexose, hexagon, 6 carbons. Glucose is actually an example of a hexose. You have a couple different ones as well: maltose, fructose, sucrose. Those are all isomers or different arrangements of this hexose. But so a disaccharide, di meaning two, it's two sugars joined together, two monosaccharides that have joined during a what? Remember, we talked about monomers becoming polymers, talked about those subunits of dehydration reaction. And this is just an example of a disaccharide. We have sucrose here, and then you can clearly see uh, this joining. And we have polysaccharides, right? Disaccharides, we have polysaccharides. Polysaccharide is just large polymers such as starch, glycogen, and cellulose. And we'll go over these individually and why they are important. But essentially, starch is going to exist in the animal state. Cellulose is going to be an important polysaccharide for plants. It's actually a structural polysaccharide that plants are going to use, and glycogen is going to be present within animals. And actually, I apologize, large polymers such as starch, starch is present within different plants. It's actually present within plants, but we'll go over that um, more later on. So plants store a large amount of glucose in the form of starch. Animals form a large amount of glucose in the form of glycogen. Glycogen is actually present within our body. And then a structural polysaccharide, cellulose, is present. We actually cannot digest cellulose. Cellulose is what is important for fiber consumption. It's actually the reason we have fiber. We can't break down the linkages within cellulose, so that is why um, um, fiber exists. That's why it passes right through us and aids in the digestive system. So this will be part one of the lecture, and then I'll finish up the second portion in a bit.